we have two definitions to look at, and with that we're going to wind up the semiconductors chapter. We're going to look at direct bandgap semiconductors and indirect bandgap semiconductors. So that is another way of classifying semiconductors. So till now we looked at intrinsic, extrinsic. Within extrinsic we looked at n-type and p-type. So that was based on the material. So if it's a pure material, it is intrinsic. If you are adding some sort of impurity, that is extrinsic. Within extrinsic, if you are adding a pentavalent element, it is n-type. If it's a trivalent element, it is p-type. Now we are going to look at another criterion of classification, and this is based on the idea of the energy difference between EC and EV and the momentum level at which that energy difference occurs. So in a direct bandgap semiconductor, the maximum energy level of the valence band and the minimum energy level of the conduction band both happen to occur at the same momentum value. In an indirect bandgap semiconductor, the maximum of the valence band and the minimum of the conduction band occur at different momentum values. So this is one momentum value, this is one momentum value. So why is this significant, or how does it matter if the momentum is same or different? So we know that there is something called the law of conservation of momentum, right? So whenever any change happens, when a body moves from one state to another, or it exerts energy, or some sort of change happens, the total momentum needs to remain conserved. So that is what makes this this concept of direct bandgap, indirect bandgap significant. So the idea is, from the valence band, when an electron moves into the conduction band, the momentum needs to remain conserved. So in a direct bandgap semiconductor, the maximum of the energy of the valence band and the minimum energy of the conduction band, they occur at the same momentum. So if there is an electron which is leaving the valence band at this point, it can straight away enter the conduction band at this point. So if it's leaving somewhere from here, it will enter the corresponding momentum over here. So momentum remains conserved without the electron having to travel much, so to speak. But in an indirect bandgap semiconductor, what happens is, your maximum of the valence band, your maximum of the valence band is somewhere, and the minimum of the conduction band is somewhere else. So the electron which leaves the valence band over here has to travel to this momentum first and then enter the conduction band. So that shift in momentum needs to take place. So recombination can occur only through a recombination center. Recombination center is the corresponding location in the conduction band where if an electron is from here, it has to enter the conduction band at this location so that momentum remains conserved. So such a corresponding location in the conduction band is called the recombination center. And first of all, why is this necessary? Conservation of momentum is necessary for efficient recombination. So the whole idea of using a semiconductor is, I want to achieve conductivity of electricity, right? So only if the momentum is conserved when the electron goes from valence band to conduction band, then only then the conduction of electricity will happen well. So even in an indirect bandgap semiconductor, I can pick up an electron from here and put it straight away here. But momentum is not conserved, meaning it will not allow effective conduction of electricity. So if I want optimum electrical conductivity, the electron has to travel all the way to an appropriate momentum location. So what is the problem with that traveling is, the time taken becomes a little more in case of an indirect bandgap semiconductor. So this topic we don't really go into much depth. It's not an in detail part of our syllabus. We just need to know the definition of direct and indirect bandgap.